The Earth we live on and the universe we live in hold an infinite number of questions. How, why, when did things become the way they are? To find the answer to these questions, men use what is called the scientific method. We observe and study the complex world about us. We ask of each thing we see, how, why, when. And eventually, ideas for possible answers to our questions are found. Secondly, we test our ideas by gathering evidence. Enough evidence for these possible answers to be accepted. A mystery, a possible answer, a great amount of study and hard work, a scientific method that has helped find many answers to questions we have had of our universe. One very old question has to do with our Earth and its land and water. Have the continents always been in one place and the oceans in the other? And if they have not, how and when have they changed? Using the scientific method, these questions have been answered with the theory of continental drift. At the turn of the 20th century, a German geographer named Alfred Wegener was studying the map of the world. In examining the Atlantic Ocean, he noticed that the coastlines of North and South America and Europe and Africa were quite similar. Could it be possible that the American continents had once been part of Europe and Africa? 3 years later, Wegener introduced his theory of continental drift, convinced that at one time all continents were united in a single land mass. He called the land Pangaea. However, before this curious idea could be accepted, more evidence was needed. In the 1950s, a group of English geologists uncovered new evidence while studying the Earth's magnetism. The Earth, like any magnet, has a magnetic north and a magnetic south. The magnetic north for the Earth is located on an island just above Canada. This is not the same as the true north, which is almost 1,000 miles away. The true north is the point on which the Earth rotates and is a permanent position. However, the magnetic north has appeared to change its location over millions of years. It was while locating these positions that geologists uncovered evidence for continental drift. To find these positions, they could not use a magnetic compass, for it only tells the magnetic north today. But they could use rocks. Lava is liquid rock that is pushed to the surface of the Earth. Contained in the lava is an iron compound called magnetite. When this lava cools below 1,000 degrees, it will solidify. When it drops below 600 degrees, the magnetite in the lava will become magnetized in the same direction as the Earth's magnet. So, if we could find this direction in these old lava flows, we should be able to locate the magnetic north, when this lava was formed. These geologists show how this is done. First, the present position of the magnetic north is marked on the rock. Then the angle of the rock is measured. All of this is carefully recorded. Finally, the rock is broken loose to be taken back to the laboratory. Here, a piece of the rock is cut into a usable size. This is called coring. Then this core is tested. This particular machine is called the spinner. From it, we can learn the direction of the Earth's magnetic field when the rock was formed. This North American rock is 500 million years old. From it, we discover that the magnetic north 500 million years ago was located in the East Pacific. Rocks from Europe and Asia were also tested, but they showed the magnetic north 500 million years ago to be in the middle of the Pacific, nearly 3,000 miles east of the American magnetic north. Assuming that it is physically impossible to have two magnetic norths, what would happen if we move the two poles together? If we move a pole, we must also move a continent. It is evident that the continents must have drifted. But how? About this time, the Navy began exploring the ocean floors. The Atlantic Ocean was mapped, revealing a ridge as high as the Rocky Mountains and stretching hundreds of miles across. It was named the Mid-Atlantic Ridge. The Pacific Ocean was also mapped. Off the coastlines of the continents, a set of trenches was found. The deepest trench, the Mariana, plunges 7 miles down. What could have caused the ridges and trenches? In 1961, while studying these maps, two geologists, Dr. Dietz and Dr. Hess, independently came up with the same remarkable idea. If we could look at a cross-section of the Earth, we would see two layers: the lithosphere, composed of hard, brittle rock, and the asthenosphere, composed of a soft, pliable type of rock. The trench Dietz and Hess proposed is formed when the lithosphere dips down into the asthenosphere. At another place on the surface of the Earth, the lithosphere spreads. Molten rock from the asthenosphere pushes up, forming a ridge. The overall result is a continuing moving plate where new crust is created at the ridge and old crust is destroyed at the trench. If a continent happened to be part of this plate, it would move along with it. Using the ridges and trenches as boundaries, the Earth was divided into a number of major plates, all moving on the Earth like slabs of ice on water. But how can we be sure this is what is really happening? Is there some kind of proof? On the ocean floor are layers of sediment consisting of sand, mud, and dead sea organisms. if the sea floor is spreading, new sediment would be settling on the recently formed crust. Thus, at a ridge, the bottom layer of sediment should be symmetrical on either side, becoming older as we move away. If we could find the age of this bottom layer of sediment, we would know for sure whether or not the sea floor is actually spreading. In 1968, the National Science Foundation began sponsoring a deep-sea drilling project. A ship, the Glomar Challenger, was built and equipped to drill into the ocean floor. Using miles of pipe, drilling was carried out at different locations across the mid-Atlantic ridge, bringing up cores of the bottom layer of sediment. A laboratory on the ship enabled scientists to examine the cores as soon as they were brought up. From the Atlantic, the Glomar Challenger continued on to other oceans, but not before firmly establishing the theory of continental drift. The results were as expected. Cores that were drilled up from near the ridge were not more than 1 million years old. However, they became progressively older as we moved away, reaching 200 million years near the continents. In 1970, using information gathered from seafloor spreading, rock magnetism, and from coastline similarities, the first maps were made in an attempt to show accurately how the continents have drifted. 200 million years ago, all land was one, Pangaea. Spain and New York were together at the equator, and India was against Antarctica. At this time, dinosaurs were beginning to roam the earth. By 180 million years ago, Pangaea had split into two parts, Laurasia and Gondwanaland. By 65 million years ago, South America had broken away from Africa, and India had moved considerably north. This is how the continents look today. North and South America have joined, and India has collided into Asia, the crunch causing the formation of the Himalayan mountains. These maps are by no means final, for the more we observe and experiment, the more accurate they will become. As we have seen, use of the scientific method has expanded our knowledge of the Earth. We know more, yet curiously, the number of mysteries have not decreased. For example, the drift from Pangaea to the continents as they are today has taken 200 million years, long enough for a mountain to form and a road away 10 times. Yet if we look at this time scale on a graph where one pole represents the formation of the Earth and the other today, we see that the 200 million years is only a fraction of the Earth's history. What was there before Pangaea, and what forces caused Pangaea to split apart? As Albert Einstein once said, as a circle of light increases, so does the circumference of darkness around it.